Hello friends, I am Chandan. In last lecture we covered that the actual efficiency is always less than equal to the maximum efficiency, or you can say that the COP, actual COP is always less than the maximum COP. So from here the actual efficiency is always, if the actual efficiency is equal to maximum efficiency, then you can say that this is a reversible engine. And if the actual efficiency is less than the maximum efficiency, this is an irreversible engine. And if the actual efficiency is greater than maximum efficiency, then this is not possible. Okay, so now let's focus on one problem. So read the problem carefully. So this is the problem. So read the problem carefully. So uh, three engines A, B and C operating on Carnot cycle use working substances H, argon and air respectively. Which engine will have higher efficiency? So this is basically a multiple choice question, and there is a uh, four answer. Suppose there is a one answer is efficiency of A is greater than efficiency of B, efficiency of B greater than efficiency of C, or efficiency of A greater than efficiency of C, or D is all the engine have same efficiency. So in last lecture we covered that the for Carnot cycle, the engine efficiency does not depends on the working fluid. So here the working fluid is argon, oxygen and air is there. So the Carnot engine efficiency is not depend on the working substance. So that is why you can say that all engine have the same efficiency. So from here you can say that option D is the correct answer. Okay. Now next question. So try to understand this question. Very easy problem. Okay. So let's try to understand this question. Okay. So read this question carefully. So uh, here an inventor claims that heat engine has the following specification. Okay. Power developed, that is equal to 50 kilowatt. Fuel burned per hour, that is equal to 3 kg. CV, that means calorific value of the fuel, that is equal to 75,000 kilojoule per kg. Temperature limit, that is the higher temperature, that is 627 degrees Celsius, and the lower temperature, that is 27 degrees Celsius. The cost of the fuel, that is equal to rupees 30 per kg. Value of power, that is equal to rupees 5 per kilowatt hour. So the performance of this engine is, there is a 4 option, that is possible, not possible, most economical, uneconomical. Okay, so just try to understand this problem. So there is a power develop is given, that is 50 kilowatt, and there is a fuel supply, that is 3 kg. Fuel burned per hour, that is 3 kg per hour. Okay, and calorific value is also there, and there the temperature limit is also there. Okay, so here, so the higher temperature, consider the suppose consider that this here temperature T1 is 27 degrees Celsius, sorry, T1, that is 627 degrees Celsius. So here T1, the temperature, that is 627 degrees Celsius. So this is basically 900 Kelvin. Okay, addition 273 273 Kelvin. Okay, and temperature T2, that is a lower temperature, that is 27 degrees Celsius, and this is basically 300 Kelvin. Okay, now the given, so let's try to focus on the answer. Okay, so here power is given, that is 50 kilowatt, and there is a calorific value and mass flow rate is also given. So from here you can calculate the heat supply rate. Okay, so calorific heat supply rate, that is equal to calorific value of the fuel into mass flow rate of the fuel. So calorific value, that is 75,000 is given, and mass flow rate, that is 3 kg per hour, that is basically 3 by 3600. So hour is converted to second. So from here you can say that the heat supply, the heat supply rate, that is equal to uh, 62.5 kilowatt. So if you want to calculate the efficiency, actual efficiency, that is equal to output by input. So from here, this is 50 by 62.5. So from here you can get the 80% efficiency is the actual efficiency. Now if you want to calculate the maximum efficiency, we know the formula, that is equal to 1 minus T2 by T1, that is equal to 1 minus T2. T2 basically, that is 27 degrees Celsius is there. So this is converted into Kelvin. So here T2 is converted to Kelvin. So here the T2 is converted to Kelvin, 300 Kelvin, that is T2, and T1, that is 900 Kelvin. So from here if you put this value, the efficiency is got, the maximum efficiency, that is 66.67%. So here if you compare these two data, so the actual efficiency is 80% and the maximum efficiency is 66.67%. So how it is possible? So that is why this engine is not possible. So from here you can say that the option B is the correct statement. So correct, that is not possible. So the engine is not possible. Okay, now let's try to focus on the another question. Okay, so read this question carefully. An inventor claims that his new concept of an engine, while working between the temperature limit of 27 degrees Celsius and 327 degrees Celsius, reject 45% of the heat absorbed from the source. His engine is then equivalent to which one of the following engine? Okay, there is a option is there, there is possible, impossible, there is 4 option is there. So basically you have to compare the actual efficiency and the maximum efficiency. Now if you want to calculate the maximum efficiency, that is equal to, if you want to calculate the maximum efficiency, we know the formula, that is efficiency, that is equal to 1 minus T2 by T1. So from here the T1, so here T1, that is 327 degrees Celsius. So T1, that is 327 degrees Celsius. So from here you can get, that is 600 Kelvin, and T2, that is 27 degrees Celsius. So this is converted to 300 Kelvin. So from here you can say that efficiency, that is equal to 1 minus 300 by 600. This is basically 50%. So from here you can say that the efficiency, that is basically 50%. Now the inventor said that here the inventor said that is reject 45% of heat absorbed from the source. So let's try to understand this case. So there is a source, and this is a sink, and there is a heat engine. Okay, there is a heat engine, there is an engine which absorb the heat from this source and reject the heat from this sink, and there is some amount of work. Suppose consider this is 100, this is 100, and here it is rejected 45%. So So this will be 45. So this must be 55. Okay. So if you want to calculate the efficiency, that is equal to output 55 by uh, 55 by uh, input is what, that is 100. So input 100. So from here you can get the 55% efficiency. Okay, 55%. So he told that the efficiency is 55%, but the maximum efficiency is 50%. So he told the wrong thing. So this is why the this is an engine, and there is impossible engine. So this is an impossible engine. Okay. So next focus on another question. So here focus on this question. Okay. Try to understand this question. So in a reversible heat engine operating in a cycle between a source temperature of 606 degrees Celsius and a sink temperature of 20 degrees Celsius, that is source temperature is given, that is T1 606 degrees Celsius and T2, that is 20 degrees Celsius. So the work done per per kilojoule heat supplied to the engine is what? So you have to calculate the work done per kilojoule heat supplied to the engine. Okay. So what data is given? So here the temperature T1, that is basically, so here the higher temperature, that is 606 degrees Celsius. From here this is 606 plus 273 Kelvin. From here you can get, that is 879 Kelvin. And the T2 temperature is the sink temperature, that is 20 degrees Celsius. So this is 20 degrees Celsius, that is basically 273 plus 20, that is 293 Kelvin. 293 Kelvin. So T1 and T2 is given. Now if you want to calculate the efficiency, that is equal to 1 minus T2 by T1 by T2. Sorry, 1 minus T2 by T1. So this is basically 1 minus T2 by T1. Okay. So from here you can say that 1 minus T2, that is 273 and T1 879. From here you can get, so efficiency we know that is output by input. So consider the output is W and input, that is in question, this is per kilojoule of heat supply. So input, consider this is 1. Okay. So W by 1. So from this you can get this data, that means 0.67 kilojoule. So W equal to 0.67 kilojoule. So this will be the answer. Okay. So this will be the answer of this question. Okay. So now let's focus on the another question. So this is the last question on this lecture. So just focus on this question. A heat pump absorbs 10 kilowatt of heat from outside environment at 250 Kelvin while absorbing 15 kilowatt of work. It delivers the heat to the room that must be kept warm at 300 Kelvin. The coefficient of performance COP of the heat pump. You have to calculate the coefficient of performance of this heat pump. So what is given in this question? What is given? The heat pump absorbs 10 kilowatt of heat. So W, the amount of W, that is equal to 10 kilowatt. So W, that is equal to 10 kilowatt. Okay. Now heat from the outside environment at, so here the T2 temperature is given, that is here T2 temperature, T2 is basically 250 Kelvin, and T1, the worm, the T1 temperature, the higher temperature T1, this is basically 300 Kelvin, and while absorbing 15 kilowatt of work. So here, uh, uh, here what is given, that is while absorbing, so here a heat pump absorbs 10 kilowatt of heat from outside environment at 250 Kelvin while absorbing 15 kilowatt of work. So here, so the Q2 amount, Q2 is, the value of Q2 is given, that is 15 kilowatt. You have to calculate the performance of this engine. So from here, this is our system. So here, focus on that. So this is our room, and this is the atmosphere. So atmosphere temperature, that is 250 Kelvin, and temperature T2, and here room temperature, that is 300 Kelvin. So W is also given and Q2 is also given. Now now you have to calculate the COP. So if this is our system, heat pump is our system, if you from first law of thermodynamics, you can say that summation of from first law of thermodynamics, you can say that, so Q2, that is conservation of energy. So this is our system. So from here, Q2 is entering to the system and W is entering to the system, and Q1 energy going out to the system. So from here, you can say that Q1, that is equal to, what is the amount of Q2, that is 15 kilowatt, plus what is the amount of W. W is basically 10 watt, 10 kilowatt. So 10 kilowatt. Okay. So from here, this is 25 kilowatt. Okay. So if you want to calculate the COP, of heat engine, this is basically heating effect by energy input. So from here you can get heating effect, that is 25 by 15. So from here you can get 1.67. This is the COP. But here the maximum COP, that is equal to, so what is the maximum COP? That we know the formula, that is T1 by T1 minus T2. So here T1 is given, that is 300 Kelvin, and T1 minus T2, that is basically 300 minus 250, that is 50 Kelvin. So from here COP, that is 6. Okay. So the coefficient of performance, so this is the answer. So here this is our answer, that is COP, that is 1.67. And in question, if there is if you want to calculate the maximum COP, the maximum COP will be like this, that is 6. Okay. So okay, this is my handwritten notes. You can download it from the description. There is a Telegram link. You can join that Telegram link, Mechanical Bengali. Like, share and subscribe my YouTube channel. Thank you.